The CNC router machine you see here is very similar to the black toe 2x4 foot model that you see on Build Your CNC Machine. It's got a chain drive on the X and Y axis and a ball screw on the Z axis. And it works pretty well. It uses V-groove bearings on aluminum channels, aluminum angles that work on all three axes as the linear guide rails. There is a deficiency that I have noticed in this design that I think could be improved. Let me zoom in here on the deflection that you get at the tip of the router when it is under load. Right now it moves very nicely, but if you press on this, I have a dial indicator over here, thousandths of an inch. If you press on the tip with a force that is similar to what you would get from pushing on the router bit on a piece of wood or aluminum, you get a significant deflection approaching 20 thousandths of an inch in each direction. That's almost 40 thousandths of an inch of play. And if you may be able to see the actual rocking motion of the head here. Now, you might think that that is due to the fact that it's made primarily out of wood and aluminum. And that, I believe, is not correct. That the 3/4 inch high quality plywood that is used in these designs actually is very stiff. It's almost as stiff as a 1/4 inch of solid aluminum. So I don't believe that that is where the problem is. The problem, as I see it, is twofold. One is on the V-groove bearings, which you can see right here, that they actually deflect a little bit. There's a little bit of play in the balls, in those bearings, and that allows motion in this direction on all three axes. And I will try to show you that in another close-up, that you can actually see that motion. If you take this bearing in your hand and you move the center part, you can actually see it move a little bit. The other factor in this design that I think is a little problematic occurs with these slotted bearings, slotted bearing location slots, where you're supposed to line up the bearing, push this up into the slot so that it's tight against these rails, and then tighten it down with a wrench while you're holding it tight. This I found very difficult because, for one thing, you can only get so much leverage with your hands. Another thing is, as you tighten, even with the washer, as you tighten, it tends to move a little bit. It was very hard to get this really, really tight. And I believe a device that could push those bolts up into the slots and hold them there, I think would be of great value. So therefore, I'm going to attempt to make these modifications to this router, and we'll see if we get any improvement in the deflection. In order to avoid having to take apart the entire bridge, I was able to, after removing the lower two bearings on each of the arms here, I was able to cut a notch using a saber saw, and that would allow access to the ends of these slots to put a set screw in. The set screw that I'm using is a 1/4 inch by 20 screw that matches the other kind of hardware that's in there, and it's just screwed right into the wood. I've put tapped the wood at the end, at this end of the slot. We're now going to take a closer look at the play in these V-groove bearings. I'm putting one of the bearings onto a longer bolt just for testing purposes, and I'm going to tighten it down. It's good and snug. Now, you probably can't see this when I just wiggle it like this. But what I'm going to do is put it in the vise here pretty solidly, and then just press up and down on the shaft here, and you can easily see that movement. Now this, because of the change in distance between the shaft and the bearing and the shaft and the end here, this is magnifying the play by probably a factor of 8 or 10. So the actual play in the bearings may only be something less than 1,000th, but it shows up significantly more than that in the application. So what can we do about this? So to take the play out of the bearing in the axial direction, what we're going to do is pair it up with another bearing, in this case a plain bearing, because they're much more inexpensive than the V-groove bearing, but the plain bearing of the same size. And what we'll do is we will load the outer races of this bearing against the other bearing, the V-groove, and in that way push the bearings apart on the outer races and squeeze them together on the inner races, because they're going to both be on the shaft here that's been tightened, and that will allow us to take all the play out of it. This is very similar to what's been done on the vertical Z-axis on board. Now, in order to find out how much material, shim material, needs to go in between these two bearings, we must do this in matched pairs, because each bearing is slightly different. So take the pair of bearings that you want to actually use together, put them on a shaft, tighten it down, and then using 2 sets of feeler gauges, get the size of the gap in there. Now this is 8/1000ths of an inch, and it should go in on one side, and I have another set of feeler gauges, and here I picked out the other 8/1000ths, and by pushing hard I can get it in there. So you want a nice tight snug fit in order to get the reasonably accurate reading. So 8/1000ths is approximately what we want for the shim. That will allow them to take the play out. Now, shim material is readily available online. I bought a pack through Amazon from K&S Precision Metals. And this is a little hobby pack. I think it costs about $4 or $5. This one comes with 1, 2, 3, and 5/1000 pieces. Just fairly small pieces, but we don't need a whole lot. And I bought several packs of these in order to have enough material to do all 16 bearings. So cutting this material out now, and I got brass because it was readily cuttable with a decent pair of scissors. I felt that that would be adequate for keeping the tolerance over a long period of time. Cutting these out, it really does work best with scissors. I have tried cutting the material with drills and cutting tools, you know, hole cutters and everything, and what you end up with is a piece of ruined material. It just can't be done. This material is too thin for the shear stresses that are put on it. So the way to handle it is take one of the bearings, place it on one of the sheets. In this case, this is a 5/1000 sheet, and just trace around it with a thin line magic marker. I mark them with a 5, so I know how much they are. And then for the inside diameter, I've used a 9/16 or so socket and mark the inside. You want something like a 5/8 to 3/4 hole so that it does not bind up against the inner race. And then using a pair of these fine scissors, you can cut out the material. I'm not going to cut this all the way out for you. One thing I want to point out is that cutting the inside is a lot harder than cutting the outside. My suggestion there is that the material doesn't have to be a complete washer, solid washer when you're done. It can be cut because it's going to be squeezed between the outer races. In fact, you could in fact just use 3 pieces of this shim material around the outer race, and that would be enough to give you the spacing, but I found that it was actually harder to work with multiple pieces than with one piece. So the trick then, I think, is to cut the outer diameter, then cut right through into the inner diameter and cut around until you have it all the way cut. Then what I usually do is I take something like my little sledgehammer here, make sure it's good and flat, and then I can use it. Now let me use 2 pieces here. I'll show you how this goes together and what you're looking for when it's all together. We measured 8 thousandths. Here's a 5, and here's a 3. I put them together, position them over the bearing, center it reasonably well before I assemble it. I always use a little washer on the inside because the V-groove bearings sometimes can rub on the nut. And before I tighten it up, I make sure that the washers, the shim material, is centered around the outside, and that's how I know that it's okay on the inside. So let's tighten this up again. Tight is the way it's going to be on the CNC machine. And let's take a look at what happens. I can still turn the shaft very easily, so that's going to allow this V-groove bearing to roll nicely along the channel. But the other characteristic is I have to be able to make these just barely turned against each other. And that means that there's essentially no play left in this. But if I try to make it so they won't turn at all, then the pressure is actually too great, and it adds up to further resistance in the regular rolling. So there's a good point here that you have to get that will allow you to get just all the play out and not put any extra stresses on the bearing. So now we will make up a whole bunch of these and we will install them in the CNC machine.